You never know, they may break off into football as we go into the basketball season here. Session 24, we're going to start off. We're going to pick up where we left off Friday with me hearing voices and music. But what I want to do is I want to finish the discussion on quality control as we start to talk about sampling procedures. Few points of clarification just for the class. There will be some exams, previous year exams posted online so that you will get access to those. The exam will be as scheduled on the syllabus, so there should be no shocks there. The exam will be open book, open notes, so you can use the textbook for this class. You can use the notes that are in front of you, but that's calculator. I don't want you printing out like ACI Manual of Concrete Practice or anything like that, but that should get you all set. So are there any questions on the exam? No, and I will ask to have the solutions, make sure the solutions get up for you. So the issue that we were discussing as we left off with class was the fact that we're sampling in heterogeneous material. And here we've got some fireballs and jawbreakers that are sampled in a 70% red ratio. And depending upon how you pull that sample, you may get a very different representation of the material. So one of the things we need to be really careful when we're pulling samples out of concrete is to really get something that's characteristic. So really the goal is to try to take a real an unbiased unit to look at. And many times this is frequently broken up into sublots and lots. So it's very frequent to try to break up production amounts based on a typical day's production or typical day's placement. So a lot of times you'll hear people breaking these into, let's say, 2,000 square yards of pavement. They'll break it up into 3 sublots. And that'll be the direction that they go for identifying payment for larger jobs. That'll also help them determine sampling frequency. They should be pulling samples. Generally, you'll see on bigger construction, they're pulling samples twice a day in that general direction. Now, a few things on production sampling. Here you can see them making some flexural testing beams. ASTM is the authority on standard tests. Now, this is for half of the industry, I would say, is dictated by ASTM. The other half of the industry is really dictated by AASHTO, which is the state highway transportation officials. You'll find that ASTM and AASHTO standards tend to be very, very similar to one another. On occasion, there's a reason that they're a little different, but generally they tend to be very similar types of documents. You will also see a lot of times that different agencies will have their own standards. So for example, if you see something specified in the state of Indiana that's specified as ITM, that stands for Indiana Test Method, and that is usually a smaller test that may have something that's specific to that region. The basic thing I want you to look at here is not to go home and memorize all the standards, because we all know that that's a really valuable exercise and you should be spending the rest of your spring break doing that. For those of you who haven't realized that was sarcasm, it's sarcasm at its greatest. If you could stay awake through 1 or 2 of the standards, that's a great feat. But the reason the standards exist is so everyone tests the concrete the same way. So we will talk later on in the semester about things that I think are wrong in the standards. That is my opinion, because I don't produce concrete for a living, I don't sell concrete for a living, I don't specify concrete for a living. I'm entitled to have my own opinion, and when we test in the lab to try to get toward fundamental properties, we may do things slightly differently. When you are testing for use in the field and ASTM is specified, ASTM is specified as written. There is not a modification to ASTM. It is the way that it is written in ASTM so that everybody does it the same way. Everybody gets the same results. There are reasons for many of the things that are put into the standards. Attention to detail is incredibly important, and I will show 3 examples here where attention to detail is incredibly important. Properly making the specimens is really vital, making sure that you use the right consolidation, the right vibration, the right finishing. Curing the specimens, properly placing them in water. Dry specimens will give you lower strengths, especially in the flexural beam test. It doesn't mean that the concrete was any different, just means that they were not adhered to, the standard was not adhered to, and could cost you money. So typically you want to test your samples wet, especially in the flexural test, because you'll get much higher strength and it's a much more consistent spec. Now, we talked a little bit about performance specifications, and really the best way to think about this is the The idea of quality control, quality assurance is really setting sort of the minimum bar that needs to be cleared. What you're doing with setting QCQA standards or QCQA values is you're saying that everybody that's out there has to jump over the medium, the lowest bar so that they've passed what's an acceptable material. It would be roughly the equivalent of all of us in this room basing our times based on how fast I'm going to run a race. I dare say that almost everybody in the room would be able to pass that without too much of a problem. Here you can see that we've got the high jumper. If the bar is set too low so that everybody can participate in the competition, you're really not seeing a big benefit to the Olympic person who's out there who wants to be competing at the Olympic level. So what you're seeing you're seeing these new specifications that are coming out, and as new specifications come out, they're really getting to the heart of the matter. It's no longer make something that looks like a cookie and doesn't taste horrible. We're going to start rewarding you for the quality of what it is that you're producing. Sampling will be a key issue, and writing correct end result specifications is going to be really a key into what you're after. Now, one of the things that we've done in the state of Indiana, INDOT has established performance targets. They relate this to measurable properties. This is one of the really vital aspects where there are many things that are missing. I would say that this is one of the trickier, although it doesn't seem like it should be one of the trickier steps. This is one of the trickier steps because most agencies haven't thought of their concrete in this way. It wants to last for 30 years. Well, what properties do we need to talk about to make sure that it's going to last for 30 years? Those properties are related. The measurable characteristics, the properties are going to be related to engineering properties and used in life cycle predictions to predict the cost of that particular structure over a period of 10, 20, 30 years. And then that cost over the next 20 or 30 years is used to evaluate incentives and disincentives for that particular concrete. Now, as this starts to come up, you're going to see a lot of questions that arise when these specifications start to go into practice. Mainly, these questions are really coming around what are the quality characteristics that we're really targeting for? What is the most fundamental way to use the material properties that we're measuring in life cycle simulations? I will say that I think a lot of the properties that are measured to get good relative numbers, and they really can't be scaled up in many cases to performance simulation models. And what I think we're going to start to see are a whole new list or a whole new set of types of tests that are out there that really get us towards fundamental material properties that can be used in performance simulations. So we're going to see quite a bit of this, I think, over the next 20 years. With that, I want to jump ahead a little bit. And I want to start to talk a little bit about the concept of the maturity method. Now, up till this point, we've really been sort of vague in how we describe the fact that the concrete is going to gain strength over time. We say if the temperature increases, it's going to gain strength faster. We've been kind of vague about this. And what I want to do is I want to try to describe the maturity method, which is one way that you can go about quantifying the influence of temperature and time on exactly how fast the material properties are developing. Now, this has a few benefits. They're mainly related into construction management issues and more rapid testing. One of the things that you're seeing people wanting to do in the field more and more frequently is you're seeing them want to get out there and get their test measurements as quickly as possible. Historically in the industry, we've been based on a 28-day compressive strength. So people will wait 28 days until they decide whether that concrete was good or wasn't good that they were using. So if you're in a construction operation that's moving somewhat quickly, you may have several stories on the building before you realize that, oh, those foundations that we put in, the concrete wasn't that good, so we've got to take it out and replace it. At that point, it's a little bit too late. So you're seeing a lot of people move to fast measures of the performance of the material. And maturity gives you a way that you can start to get toward that. What I want to do is I want to provide a little bit of the background on the use of the maturity method. I'm going to cover the background, especially as it relates to the nurse-saw portion of the equation. We'll talk a little bit about some applications in field equipment, talk about how the chemical reaction is modeled, how strength development is modeled, talk a little bit about some of the models of transformation, the hyperbolic and the KMAJ models in particular, and then we'll get on into a few of the advanced topics, which I think, at least to me, are somewhat interesting, and I hope to you at least have some value as we start to go throughout the rest of the time. Now, a few years ago, we started to see what is the way that we can try to relate concrete back to something else that a lot of people have a lot of experience with. And it was about the time when I had a postdoc, and he happened to be from Italy. It was World Cup time, so every day I would hear about some country beating some other country in soccer that I really could have cared less about. And then unfortunately the Italian team made it to the actual World Cup, and I had to hear about this now for every single day, and how the Italian team was so fantastic and they were so great. So I finally went and I watched the World Cup, and I got inspired. I said, now I catch it, I get it, I understand why people are excited about this game. And I went out with Max the dog, and we went to try to play soccer in the backyard, and our grass looked a little bit like this. And it was a little unfortunate. So I said, well, we can't play soccer on a field that looks like this. It just wouldn't work for us. So we said, well, how do we go about putting grass in here? Well, we could go and we could get instant grass. All right, but that's probably not what most people are going to do. We could really go old school. We could go down to the Home Depot or the Lowe's, or whoever wants to endorse this particular part of the lecture, please let me know. You could go and you could pick up some grass seed. And the big issue there is you want to make sure that that grass is going to grow really fast. So the fastest grass that you could probably get is this grass right here that comes from Turfline, Fast Start grass. All right, you know that this is going to hydrate really quickly. You know that there's going to be that grass really taking off. You're going to have a nice coverage. Max and I could be playing soccer by the end of the day. So we went home. We tilled up the backyard. Went out there. That's a picture of me in the sunlight. Maybe not me. Fertilizing the backyard. I added a little bit of water to it. And then we started to grow. All right, and the question is, how is this at all related to the topic at hand? All right, how is this at all related to concrete? Well, the real question is, how long would it take this grass to grow? And if I asked everybody here, how fast does grass grow, most of you would probably look back at me and you would say, I have no idea how fast grass grows. How do you quantify it? It depends. What are the conditions? What's the temperature? How much moisture does it have? Where is it? Is it in the shade? Is it in the sunlight? And if you flip over the back of the fast grow grass, you see a graph that looks something like this. And it's fantastic because it's one of those graphs that really has absolutely no meaning to it. There's absolutely no units on the y-axis. Just tells us about the growth rate. So you have no idea what the scale could possibly be. And then you've got the growing months that are listed here along the x-axis. And one of the things I always like when we list out the months is it spells my name. And I always find that fascinating. Just a couple of years ago, I figured that out and realized that that corresponded to the months of the year. But essentially what you can notice here is that the rate at which grass grows varies depending upon the month. Does that make any sense? Yeah. Why would it vary depending upon the month? Mike says yes. I would dare say some people would say no, it shouldn't be dependent all on the month. So it depends really not only on just the month, right? The idea of the greenhouse is you're going to have some environmental conditions. So what we did was we sat down and we looked at the temperature range in the state of Indiana. So we've got the temperature in Indianapolis. It's given in Fahrenheit, good old-fashioned U.S. units over here, so we all know what they are. Maximum and minimum. And if you overlay this on top of the previous graph, you will find out that there is a correlation of some sort between the growth rate and the temperature at which the grass seed would actually be utilized. So we could start to say that there's a relationship here, and this is a relationship that is not only going to hold true for grass, but it's going to hold true for our cement. Our cement is going to grow proportional to the temperature at which that cement is being placed, to the temperature at which that mixture is being stored at. So when we start to look at grass like we saw this one here from the 1950s, where we saw concrete at 38 degrees Celsius, gain strength very, very quickly. Concrete at a lower temperature takes its own sweet time and may take 28 days to come up to strength or 90 days to come up to strength. We could actually start to think about a theory that would predict this stress development by understanding how temperature comes in and impacts the overall performance. So all of a sudden we could start to take some of these concepts that we saw with the grass, that temperature is going to be related to growth rate, maybe moisture conditions are related to growth rate. We could say that both of these are influencing the rate of reaction that's taking place inside of our cement. And this really leads us into the idea of the maturity concept, and frequently you'll hear this referred to as the nurse-Saul relationship. So since the early 1900s, there have been people who've been seeking a relationship between the temperature and some material property that's developing, and I would say the material property most frequently used is strength. However, I would say that there are a lot of people looking at other properties that are developing and trying to use these maturity concepts in great detail. This really took off in the 1950s with the real rapid growth of the precast and pre-stressed concrete industry. They wanted to try to turn the formwork around as quickly as possible. They wanted to heat up the concrete, and you'll see people like McIntosh, Nurse, Saul, Plowman, all trying to do something to try to develop an equation that was going to work better to try to predict how fast the strength was going to develop in their particular concrete. Accelerating curing is really the driver. So the basic idea is they wanted to be able to produce some sort of a concrete in a factory, heat that concrete up with some steam or place it in a heated tent, capture the heat, and see how fast the concrete is going to try to develop strength. Now, McIntosh used the product of time and temperature, and we will see this coming back and forth. Time times temperature is typically going to be referred to as a value of maturity. It's typically a way that we're going to start to look at maturity. They tried a basic datum temperature, and this is going to be one of the things that we'll come back to, but they basically said that we're going to assume that this reaction takes place anytime the temperature is above -1. If it's below -1, we don't have to worry about that reaction. So they start everything at -1 and they go from there, and then they reported that it didn't work real well. Nurse reported that it worked great for him. He used a slightly different approach. He reported only the air temperature, which seems like it would take it further away from working. Didn't use a datum temperature, but it seemed to work just fine for him. All right. Saul suggested that the datum temperature was needed, and he proposed linking time and temperature through maturity. So here you can see three people coming up with very different beliefs on what's working and what's not working, and we'll start to see why some of these concepts do work and don't work. But the basic idea here is they want to take time, they want to multiply it by temperature, and they want to use that as an index, and they're going to call that index maturity that tells us roughly how much of the concrete, how much of the reaction has occurred inside of the concrete. So earlier in the semester we talked about degree of hydration. And degree of hydration was what?
How much of the cement has reacted?
How much of the cement has reacted? So you start out with 0 degree of hydration, none of the cement has reacted. 100% of hydration, all of the cement has reacted. You've got a structure inside of the material. What they're saying here is the rate at which that reaction actually occurs, the rate at which the material hydrates, is going to be related to the temperature the concrete is conditioned at. So maturity is defined in the dictionary as the quality or state of being mature, which was actually quite eye-opening to me. All right, completed some sense of natural growth or development, low but stable growth rate, an older adult, or due for payment. What we're really talking about here is this idea of some sort of natural growth and stable growth rates. So what we're basically going to look at here is the fact that the growth rate can be related back to the temperature. So the rate of strength gain, or the rate of reaction that's taking place, is related back to the temperature of the concrete. And Saul had a quote that essentially came out of one of his early papers where he said that concrete of the same mixture at the same maturity, reckoned in time temperature, has approximately the same strength, whatever combination of temperature and time go in to make up that maturity. Now, I kind of like it because I just like the idea that anytime you can throw the word reckon into a scientific paper, I think that's a good thing. All right, so if you can reckon time and temperature together, all right, what he's basically saying is he's going to come up with an index that's time times temperature. And he says that irrespective of how you got there, 5 degrees at 10 days, 10 degrees at 5 days, 20 degrees at 2.5 days, provided that maturity index is the same, provided that product is the same, you should have the same strength inside of the concrete. And this starts an interesting discussion on this strength development. It also starts to answer a lot of questions. Right? As you start to drive home today, you will notice, some of you, You'll pass signs that look like this one. There's one right out on Northwestern Avenue. Gives you the time and the temperature. You'll notice that you probably have some sort of an indicator in your car or at home that time and temperature are always related. Right? One of the things that I found really interesting is one night I was driving home and it was in an ice storm from Indianapolis, and I must have passed 40 different banks on the way home. Every single one of them had time and temperature listed, and the temperature was anywhere between 22 and 55 degrees. So I'm not sure that these temperatures on the bank signs are real accurate, but time and temperature are linked. So I think we can take something from this bank sign, we can take something from the maturity concept, all right, and we can start to put these together, and we can start to try to use this to predict the overall maturity of our concrete. So in general, if we measure the temperature development on our concrete, we would see this high peak of concrete at early ages, and this high peak is occurring because it's going through the rapid hydration. We're in stage 2, going into stage 3, into stage 4. We have a lot of heat release, a lot of reaction taking place, so there's a lot of heat of hydration that's given off. Over time then, we start to see daily variations in temperature that have to do with the ambient temperature. Now, what we're really saying here is you could draw a datum temperature. You could essentially say that all the hydration reaction stops at a particular temperature, and let's just say for the sake of the rest of this lecture, we will assume that temperature to be minus 10 degrees. That's a pretty realistic number based on what a lot of people look at. We can argue, is it minus 8, is it minus 12? I would say minus 10 degrees is a pretty reasonable number to start looking at, somewhere around, I believe it's 20 degrees Fahrenheit in that general, 15, 16 degrees Fahrenheit in that general range. And then what you can see is we are going to take the product of time and temperature. Here we're going to integrate the temperature, the difference between whatever temperature we're measuring minus the datum temperature. We're going to integrate that with respect to time, and at any point along here, we could calculate out what the maturity is. So maturity is simply the area under the time temperature graph. Now many of you have looked at this equation, and you say, I recognize that snake. I saw that snake type thing that was in that equation, but it's been about 4 years since I've actually had to solve an integral. Is there a simpler way to do this? If I can't do it in Excel, it probably can't be done, so I will say that you could do this in Excel. We could replace the squiggly snake integral sign here by a term that we may be more familiar with, and that way we are going to replace it with a summation sign. And this is the way that is most frequently done in practice. You're not seeing a lot of people sitting down with a good differential equation along the side of the road, all right, trying to solve it. What they're going to do is they're going to break the temperature up into small segments. In the lab, you may see something like 5-minute or 2-minute integrals. Out in the field, you may see 2-hour, 3-hour intervals. They're going to measure the average temperature over that time, multiply it by the time interval, and they are simply going to get their maturity index. So here you've got T0 being the datum temperature. Only temperatures above T0 correspond to strength development. The summation is an approximation of the integral and basically gives us an idea of what's developing here. So what are some of the ways that this is going to be used? They're going to be measured in the field. Some of the motivations for trying to use this in the field, right? Minimum strength required for construction operations. Right? When can we move the forms? When can we remove the formwork? When can we jump the forms? When can we move ahead? Maturity can give you some information on that. When are we going to be able to post-tension our concrete? We've got our concrete out there. It has to get a minimum strength before we can post-tension it. When can we start to go out and do some cold weather protection? When can we open a pavement to construction traffic? There are a lot of different questions here that can be asked if you have some indication of how fast that concrete is gaining strength. And some of these are things that people are very eager to know that information because it's going to change the construction process. Post-tensioning. When can they release the pre-stressing on a beam? When can they strip the forms? When can they open a pavement to traffic? They want to be able to calculate this fairly quickly and don't necessarily want to just sit there and test beam after beam after beam and try to guess at when they're going to get enough strength. Agencies will test companion specimens. How do you correlate what's happening in the field at one temperature to what may be happening at another temperature? And then it helps to limit some testing, especially in cases where testing can be costly. All right, there's a certain value associated with testing every concrete cylinder, and this is a way that you can get a little bit of information to make sure that everything's going okay as you go through the process. Now, the general approach for using the maturity method is simply to take a thermometer and plop a thermometer in a cylinder, hook that up to a maturity computer, and I will say here this is nothing more than a data logger that is essentially monitoring temperature and keeping track of the temperature. And what we're going to be doing is at different maturities, we will pop the cylinders, break the cylinders, and get the overall strength. So we'll do this a few times, and then once we've done that, we can fit some sort of a relationship to how the concrete develops strength, and this is generally referred to as the master curve. This is generally referred to as sort of a characteristic curve of the overall mixture, so that if we know the maturity value, typically this is done at 73 degrees in the lab, we have a certain set of different times that we're going to do, we can find a response that tells us how that strength develops. Now, the real power of this technique comes in when all of a sudden in the field you can measure, use a thermocouple to measure the temperature, log that temperature, and compute the maturity. You can now come back to this graph, enter at the maturity on the x-axis, where it intersects the curve, all of a sudden gives us an idea of what the strength is in place in real conditions under real temperature conditions in the field.
How would the curve differ if you were to use like field cured cylinders as opposed to laboratory cured cylinders where your temperature is not going to be the same for every cylinder, just the temperature? Like if both variables in maturity varied, how would the curve change?
In theory, the curve would be the same, and the theoretical side of it, the curve would be exactly the same. I will say that you will get some differences, especially if the temperature is really high. So the few things that are going to influence this, and we'll go through this, but high early temperature. Okay, so if the temperature is too high early on, we get that effect that I believe we're referring to as the Tetris effect, where the microstructure really can't develop. You remember I showed you some plots of the long-term strength. You just couldn't achieve the long-term strength. So that effect will kick in, and you'll really limit the long-term strength. The other effect that we typically get into that I think is a little bit more significant in field-cured concrete is the idea of water. Now, one of the things, and I haven't said it yet, but I'm building up to it, so I'm going to sort of blow the punchline of the lecture here, but the whole idea is we are making the assumption that there is enough water. So we said that there were three main ways that we could three main aspects of curing. We said that time was one, temperature was another, and an adequate supply of water. And we had to have all three of these coming together. Well, we're just going to assume right now that our field-cured concrete has plenty of water. If the water goes away, you're obviously going to alter the hydration reaction. So those are some of the things that you need to be aware of: the high early temperature issue and the water issue. If you were to do this at, it goes to 70 degrees, 50 degrees, 70 degrees, 50 degrees, you would get the exact same curve within experimental error. Okay. So unless you get to real drastic differences. Mike?
Who's going to have this information in the ReadyMix guy?
You'll see different people with it. Sometimes the ReadyMix guy would have it. Typically, the ReadyMix guy is not going to do this unless it's for a real big mixture, typical mixture they're using a lot of, and someone else is going to use this. If you're seeing a paving contractor where they're using their own mixture consistently, they will have this mixture. For example, in the state of Indiana, they can open to traffic based on maturity results. So I would say every contractor I've ever talked to knows their maturity relationship up until it hits 550 psi, which is the time they can open to traffic, because that's what they really want to be able to do.
Yeah.
Isn't this highly dependent on the level of quality control and being able to reproduce the same mixture?
Well, that's the other big caveat in this. You have to assume the same mixture. You have to assume. So the third thing, we said high early temperature, field water cured, and then same mixture. And we will actually talk a little bit about this. And you may say, well, that seems obvious. Of course we would use the same mixture. I will say that there are several states that are getting this wrong because they are not holding the contractor tight enough on that particular aspect.
At what time would you measure the temperature?
You have to measure the temperature continually. Okay, so what you're going to miss out on is the first, let's say it's going to take you 30 minutes, 45 minutes, an hour to get it into the forms, 90 minutes to get it into the forms, something like that. During that time, there's not a whole lot of temperature development because remember your concrete is in stage 1 and 2, right? So the rate is pretty constant and you're not really setting up the overall material. And we can actually argue about when it should start based on placement and some things like that. But it turns out in the general scheme, that part is really sort of insignificant because if you look at an hour times 15 degrees, it's really small compared to what you're looking at 28 days or something like that. But you need to be monitoring the temperature continually when you're doing this. Okay. Other questions on this? All right, so we'll jump in and we'll look at a few more of the approaches, and then I will come back and talk about these caveats because while some of them seem relatively simple, they may not always be. That may not always be the case. And we'll talk a little bit about some of the things you should be aware of in the field. So the typical type of application that this might be used for, I think, Mike, you were asking, is a ready-mix producer going to have this or is a contractor going to have this? If you were doing a construction site like this happens to be in the northern part of the U.S. This is a hospital. One day it could look like this. Imagine it got cold out. Next day it looked like this. How does the concrete respond in that particular case? What is going to be the strength development? How does that alter what the construction crews are going to be? You need to be able to have a way of calculating that. So I mentioned the paving industry is going to be using this enormously. You can't see it, and I can't even find it right here. The only way I even know that it's here is you can see here we've got a bright orange spot. The bright orange spot meant don't rip up the thermocouple wire that's underneath the paver, and there'll be a thermocouple attached, and I believe it was attached, I'll draw it right there. It was attached on one of the dowel bars so that we get the temperature in the middle of the pavement as it goes down. This is the I button, which is actually, so here you can see, I don't even have to draw this one in. Here you can see the I button attached to the dowel bars. In this one particular case, it's connected to a cord. This cord can plug directly into your laptop so you can download the data from this sensor very quickly. So the basic idea is it's going to have some onboard storage. On the side of your pavement, you're going to have a LAN connection. You can pull up your laptop, stop as you're driving down the road if you really wanted to, hook up your laptop, and then you get all the time temperature data at that particular point. There are people spending a lot of time now looking at wireless ways to get this information back so that they don't have to necessarily be going up and down the pavement to pull this information off. Give you a little bit of an idea on the size. This isn't one of my trick quarters. This is an actual quarter that you could use in a vending machine. George Washington on the side. So it gives you a little bit of the size and the scale of one of these temperature sensors.
How expensive are they?
It depends completely on the sensor. We use some in the lab that are nickel a piece. They'll use some that are $40, $50 a piece in the field. Okay. The question is really, I mean, as you go to higher and higher costs, are you dramatically saving costs in labor, installation, things like that? And more importantly, a lot of times the sensors that you're using are dictated more by the data acquisition system that you've got. If you were to start off today buying, a system, you may buy something very different than you bought 4 years ago or 5 years ago just based on what's out there. So the paving industry is going to use these mainly to determine the time that they can expose the pavement to traffic. And here the traffic is going to be using the pavement as a haul road. It makes a big difference to them whether they can drive the new pavement or new concrete out on top of the old concrete. And most of the times they will want to try to do this. Their goal is to try to hit the right strength, which happens to be 550 psi, in a normal construction sequence. So they want to, in 24 hours, be able to get trucks back onto that pavement. And they want to be able to determine that somewhat reliably. And if they're not going to hit it, they want to know early on so that they can call off the next day's construction operation and take it from there. Okay, so the majority of equipment that's out there is temperature-based. Now, I will show you one or two systems that are not temperature-based, but by and large, other than a few oddballs, people who spend a lot of time getting really excited about maturity, like myself, most people, when they say maturity, they are talking about temperature. They're talking about measuring temperature. They're talking about the time-temperature relationship. Many of these are reusable probes. As I mentioned in the lab, we use a simple thermocouple wire that, while the probe itself is technically not reusable unless you break it out of the concrete, you could snip it off with wire cutters, get a soldering iron out, and you've got the exact same probe, only it's 4 inches shorter than it was last time. So there are a lot of probes that are like that. There are different types of systems. There are some that are just single channel systems, some multi-channel systems. You'll see some of these systems that give you 30, 40 readings at a time. Some of them have their own onboard data acquisition, record the information, spit it back to you. We'll show a little bit more about this. There's some other devices available. I'm not going to spend a lot of time. Here's a wide range of the different pictures. You can get these in all types of different operations. They're available from most of your different manufacturers, whether it's James Instruments, Gilson's. You'll see different types down here. Basic idea here, you can see a thermocouple plugging into the side. This thermocouple wire will be put into the field. Here you can see this one actually where the probe would go in the field. Here's one that's more variable or embeddable type device. Lots of different devices. The Comameter is one that I was talking about that's not temperature based. It's based on a slightly different principle. It's based on chemical shrinkage. We're not going to spend a lot of time because I'm not aware of lots and lots of commercial application of this in the U.S. If there's somebody that's out there that's using this every day, I apologize that I'm unaware of it, but most people are doing time temperature type work. iButton is another one that's recently gained a lot of interest. Here you can see it. It's in its sort of opened up state. It's basically in its own little can, like its own little I don't know, canister. I'm searching for the better word to use, but it's a can. It's a little can. It's about the size of a quarter. Basic idea is it's going to have its usually it's going to have its own battery in with it, and then you're going to be able to interface it either with a direct line, or you'll be able to use some radio frequency type responses to get it in sort of a wireless type of application. The big thing that I would say here is you're seeing that these costs are going to be a little bit higher than what you're seeing with a lot of the other sensors. And you may say, well, $50 doesn't sound like that much. If you are paving and you're dropping 5 or 6 or 7 of these in every single day, in the grand scheme of things, it may not be that much on a paving project. But if you're looking to try to be the low bidder and you're dropping 5 of these in at $100 a day, and you're doing that over the life of the project, it adds up very quickly, especially compared to the guy who might be using something that's hardwired at 17 cents. So it's a big difference and something you need to be aware of. The big benefit here, especially if you can do it wirelessly, you can get that information. You can be making decisions as you're moving down the road. Modeling approaches. One of the things that I'll talk a little bit about. This is a slide that I've used actually quite a bit in some different classes. The whole idea of everything that we're doing mathematically, the whole idea of everything you've done over the last 5, 6, 7, 12, 34 years as an engineering student is really trying to create mathematical models that approximate the real world. So if I was to say to you, how would you model this building? At this point in your career, some of you would not blink twice about saying, well, I've got wind blowing on my lovely 3-story red brick building. That could be just about every building on campus here. And I could break this wind up into distributed forces that are acting on a cantilevered beam, and I could go through and I could solve this. And many of us would sort of take this for granted. Now, when I show this to sophomores, they're sort of mesmerized at the fact that you could actually use this because it looks kind of like statics, and it's being taught in another class now. So they're really excited about this. But you've learned over the last few years that you are going to develop mathematical models to describe how forces act on a structure and cause deformations. We are doing the exact same thing here, only we're talking about material properties. And as mentioned before, we need to understand the approximations that go into this. We've talked a little bit about some of the assumptions. We don't have real high early temperatures. The specimen's getting enough water. It's the same materials. But we need to understand these approximations because these are where people are going to get into trouble. When people start making specifications, standards, and they don't understand the specifications, this is really where the trouble is going to break out. So the basic idea here, and I always love this sign. I got this one from Federal Highway Administration. This was an actual real-life highway sign. I love the fact that if you're going too fast, you don't have time to read all the letters in the word slow. So we'll just abbreviate it. And if I was going to abbreviate slow, that's what I would do. I would take that off. But the basic idea here is you're going to break this function up into, you're going to say that the rate of strength gain is going to be dependent on the property itself that you're looking at and the temperature. So we're going to operate first on the temperature portion of this response. Now, the reaction rate, essentially when you hear people throwing out reaction rate kinetics, there are a few people who like to throw these terms around, and they like to throw people off to think that they're doing something that's much, much greater than what everybody else in the world is doing. They're essentially looking at the speed of reaction. That's all they're looking at, is how fast is the reaction going. So normally if we were looking at speed, if I asked you to define speed, you'd be saying change in position versus time. Here we're really looking at the change in reaction that's taking place over time, and what engineers are typically worried about is not necessarily how much of the chemical reaction has proceeded, but how much strength have we gained over that last period of time. All right? The theory here is that the extent of reaction can be directly related to strength. Now that is a huge caveat in my opinion, because this is not always the case. And I've made several cases, or tried to make several cases, that it's more complicated in describing concrete materials. We're typically talking about the cement that's reacting. We're measuring how much of the cement is reacting and how fast that cement is reacting. Right, so that's essentially what we're looking at here when we start to talk about reaction rate. It is highly dependent upon the properties of the cement. Right? So we will actually find properties, or we will find coefficients that describe the cement that we're using. We will describe the temperature dependence and the temperature dependence on the growth processes. Now all of this comes out of an equation that's referred to as the Arrhenius equation. So since we're going to be talking about the Arrhenius equation, it actually makes complete sense that this is a picture of Van Hoff, exactly. Arrhenius. No, this is Van Hoff. So it turns out that in life there is a huge number of processes that share this common feature. Chemistry. Lots of reactions are dependent upon the temperature. All right. It turns out that in many cases the process is related exponentially to the temperature. And one of the first people to describe this and to see this was a guy named Van Hoff. And here's a picture of Van Hoff. So you would think that this expression would be referred to as the Van Hoff equation. Unfortunately, Van Hoff wasn't really good at making practical use of this. The guy who was really good at making practical use of this, all right, was a guy named Arrhenius. And Arrhenius basically sort of had projected that he could do some of these different ideas. He was mainly worried about gas molecules. But he basically said that before a reaction could occur, there had to be a certain amount of kinetic energy that was available to propel from one chemical state to another. And while the language has changed and we have a little bit better idea of what he was trying to say, the basic idea here is that you have to have a certain amount of energy that has to be overcome to change to another energy state. One of the things that I find somewhat interesting is Savant's ideas were so out there that not only did his thesis committee give him a hard time, but they felt the need to humiliate him for proposing such a ridiculous theory and a ridiculous topic in 1886. I always find these stories interesting. It's 16 or 17 years later where Arrhenius says thank you to his committee and picks up his Nobel Prize because his ideas were so far out of the box that it actually turned out he was doing something that was useful. The Arrhenius equation is given here in sort of its general form, where we say that the reaction rate is going to be related to an exponential relationship that describes the gas constant, the temperature, the activation energy, and then some factor that's really a constant that describes essentially what we're doing. Now, most people will generally have a little bit of an issue with this, so I'm going to try to put this into the concept of activation energy. I'm going to put it into concepts that we all understand. Here you can see Max the dog and I. We are cuddled up, as we do frequently in the fall, watching a Penn State football game. We are pointing out something that's happening during the game here. Max is very eager to try to see his way around a block. Obviously, he's looking at what's happening. Now, later on that day, I will have gone to a lower energy state, and I will be now asleep on the same couch. I'll wake up, and there's some cheesy infomercial that's taking place, and I think we've all been there. It's late Saturday night, you're asleep on the couch, and you are trying to make the final decision. Is it worth expending the energy to get to an even lower energy state? All right, and that's really the question that we're after. Here we can see several different energy states. I can't say that watching football is a terribly high energy state, but we will go to an even lower energy state while we watch the movie. And then in order to get to an even lower energy state when we go to bed, we have to expend some energy to walk down the hall. Okay, so we will stand up, walk down the hall, expend some energy with the goal of going off into that deep, deep slumber, not to be awakened until late, late Sunday afternoon, where we have to come back to the earth and put together a lecture for the next day. All right. Now, if that's an example that you can't come to grips with, you say, I have no reference for what a couch would be. I don't understand the idea of falling asleep on the couch. I will give you another example that I think might be a little bit easier. If we want to take this boulder from here to down here, and we will need to go over this little hill to get that to happen, we have to expend a certain amount of energy to take this boulder up over this particular point to get it to come down to a lower overall energy state. And through the power of animation, I've done that for you. So if you don't like the analogy of laying on the couch watching football, here we are rolling boulders over little tiny hills in very artificial conditions. What we are having to overcome in this condition is the idea of this activation energy. There has to be some energy that has to be overcome to make the reaction go forward. The basic idea here is that we've got a minimum energy for reaction at high temperatures. There's a lot more kinetic energy in the system. It's easier for that reaction to take place. It's going to take place faster than it's going to take at lower temperatures. This is the basic idea behind the Arrhenius equation. This is the basic idea for where all of this comes from. We will talk about the activation energy of the cement paste reaction down here. We will talk, obviously all of us know the gas constant, all of us know the temperature. All right, but we will also see other terms get introduced. Turns out, since the gas constant is simply a constant, you will frequently hear people in the cement industry refer to this Q factor, which is simply the activation energy over the gas constant. One of the real reasons I think the cement industry loves this idea is because it takes us far, far away from scientific principles and makes it look like an empirical constant that doesn't relate to anything. And then we say that must be good because we measured it exactly for our material, and what we're measuring can't be wrong. We're not going to deal with any of that theoretical stuff. We're going to measure that Q value directly. Now, if you plot this rate constant for different temperatures, what you will actually see is that you will see a somewhat nonlinear relationship for many of the materials. And this starts to point out that some of this earlier stuff that we were talking about, of just the time times the temperature, it's not necessarily a completely linear relationship, and depending upon the type of cements that you're using, you could see a slightly different response at different temperatures. So you will see a modified version of this Arrhenius equation going in, because we're typically talking about comparing whatever rate we want at any particular temperature to the rate at the reference temperature. So we will plug our temperature in degrees Celsius. We've got our 273 to convert us over from Celsius to Kelvin or Kelvin to Celsius. We've got our activation energy divided by our gas constant. And then we will have the temperature wherever it is that we want to know our particular concrete, so that we are looking at a difference in the temperature in that particular range. So the basic idea here is that we can now all of a sudden have strength development curves for our different concretes stored at different temperatures, and we can say that the initial slope of this line is related to the reaction rate. So all of a sudden now we can find the slope of this line, we can call it K, and we can say that this is equal to this term that we had just described, which can be described by Arrhenius' equation using this activation energy and our gas constant. Now, in the 70s, there have been different terms that are thrown out there. In the 70s, Freisleben and Hanselin suggested these different values, suggested two different values depending upon the temperature. In the U.S., you're going to typically see a number between about 40,000 and 50,000 joules per mole. These are slightly higher than what you would get if you used the Nersol approach, but in general, these are some numbers that people are typically fairly familiar with, 40,000, 50,000 joules per mole. We will start now, next class, to talk a little bit about the strength development curves that are going to be used, and we'll take it from there on Wednesday.